start, so I leave you. Okay, thank you very much.
Hello out there. So today's webinar is about lasers and what is needed to build a laser and how it can be used in university for teaching or for student use. And the first kind of laser I have just put in front of me, as you can see, a helium neon laser is a gas laser having a discharge in a tube. And of course, laser is always about light and a beam of light. So let's make that visible. So can we go to camera number 3? Here you can see a look into the resonator. This is the end of our helium neon tube. Here we have the mirror, and if I now take some smoke, and somebody would please be so kind to switch off the light. Here you can see there's a lot of smoke particles in the air, and the laser is glowing very, very brightly inside the resonator. So that's just for the show effect of it. And now let's have a short introduction of what we are doing today. So I'd like to talk about helium neon and neodymium YAG gas lasers, and we'll discuss very shortly what a laser is and the helium neon laser in more detail, diode laser, YAG laser, and in the end we can discuss what is going on in your lectures or your students' labs. So, a laser. You all know this light amplification by stimulated emission of radiation, but what does it mean in detail? It's a gain that light experiences when it passes through a medium, just because there is more excited states in this medium than there are in the ground state. So a photon passing through this medium can trigger the release of another photon, and that's just what we call gain. So the light is more intense when it comes out of the gain medium than when it enters the gain medium, and some lasers just need that. They are so very high gain that you can have a laser of 20 centimeters, and just by spontaneous emission in the beginning is amplified, and at the end there is a saturation limited pulse. No optics is needed at all. And for example, in the old days, a nitrogen laser was published in Scientific American, publication more for the public, and a lot of people built it in 1974. Nowadays, working at a Bloomline spark gap with some 10 kilovolts or so, everybody would call the authors crazy. Okay. So in the more interesting part for the physics, we have lower gains, and especially in the helium neon laser we have a quite low gain. For the neodymium YAG it's not that much, but we need to find a clever way on how to improve this gain amplification, and the answer is quite simple. We have a mirror and build a resonator around it, and we use the gain medium several times when the light passes through. So every laser we present today consists of such an optical resonator, just a pair of mirrors, and a gain medium. So the typical laser properties like spatial and time coherence, and especially the longitudinal mode spacing, are related to the resonator and not the lasing medium itself. And we'll show that later. Talking about the mirrors, we have a concave or a flat concave. Today we'll have only the flat concave one. And stability means that the light must not escape, which will happen when the length is larger than the radii. And of course, as you can see as drawn, none of these resonators is stable. They have to be much shorter. And that's what we'll see in the experiment. And yeah, there's a question for didactic use. Shall we optimize the laser for light output, or shall we better care about the eyes of the student and keep it safe? So the resonator is acting within, but there is not much light coming out. You did see it in the beginning when I put my smoke inside the resonator. There's a lot of light going on, and a short calculation tells me when I have something like 0.1 milliwatt, which is eye safe at the outside, but I have a mirror which is highly reflective. There is about 1 watt of laser light in the inside of the resonator, and that was exactly what we have seen with the smoke in the very beginning. So there is much light going on, but it's not coming to the outside, so students can work with it, and when they try to extract this amount of light, the laser switches off, because it needs this resonator structure to get the gain. Yeah, so some more advanced topics I will not cover right now is Einstein coefficients, it's spontaneous emission, it's forced emission, it's absorption, and what we need is a so-called population inversion. And how to achieve this is either by a gas discharge, as in the helium-neon laser, current in a semiconductor structure. We later have the neodymium pumped by a diode laser. And optical absorption is, of course, another way to create such a population inversion. For the population to be feasible, we need some kind of bottleneck state, which keeps a long lifetime. And I think if I have the time, I can show later in this webinar. And for the rest of it, well, things are more for the university lectures, talking about 3 or 4 level systems and whatever is there on magic behind running such a laser. So first laser is a helium-neon laser. We have a gas discharge in a small glass capillary powered by 2 kilovolt power supply at about 5 milliamps. And the tricky thing here, no, it's not tricky, but the students shall learn how to align a resonator and how to align a laser, that it does not work right from scratch, but the components are needed to be put in a special way. And the way to do this is to have a green laser pointer shining through the mirrors, just because the mirrors are optimized for the red laser light, and the green laser will aid me in alignment. And now enough of theory, and let's go for the real life. Thanks. So here I am back again, and as you can see, the gas laser in front of me is still working. And on the camera number 3, you can see we have a reddish light coming out of the laser. And if somebody would be so kind to switch off the light again and leave it off. Thanks. You can see there are still some dust particles in the air, reflecting my intense laser light, which is, as we have calculated, about 1 watt of intensity. But if I try to put my finger in, well, just the laser goes off, nothing happens. And outside, if I take a close look on the end of the mirror, here you can see on the card is just a low intensity reddish dot, which is eye safe. So there is no problem for the students in order to observe it. So going back to the total view, what components is this laser made of? Let's switch it off and take it apart. We have our gas discharge tube here. We have our 2 mirrors. This mirror on my right hand is a flat. The mirror on the mirror on your left hand is a flat. The mirror on your right hand is a curved mirror. And these two form the resonator. And as we are working on an optical bench, they can remove too. So everything that's now on the optical bench is just my greenish pilot laser. And this greenish laser is giving me the aid of alignment, simply because the light coming out of it is by definition a straight line. And what we are doing is we are taking all our components, put them on the optical bench, and make sure light passes through our components. The capillary has a diameter of about 2 millimeters. And of course, since the laser has been aligned before, light is passing through, and I can have a look either on a card, or I can use my camera, turn it around, and have a look at the distant wall. Zoom in a little bit. And here you can see the spot of our laser going through the capillary tube. And if I mistune my tube, you can see I get some reflection on the inner wall of the glass, which is now completely ruining the laser beam. And if we can go to the total, you can see total. I'm just working on these two screws and going back to the detailed view. I can focus, no, not focus, align my beam back to be aligned with my laser beam. So now I have a tube that can be used in this setup. I can remove that tube. Second step is to put in the mirrors and to create a so-called resonator. And as we have talked about before, the greenish laser is able to pass the highly reflective mirror, but it is highly reflective only in the red. The green light can come through. And now we can have a close-up view of our first mirror. Sorry, here we are. And with a little bit of time, the camera is going to focus. Okay, so here we see two greenish dots, and one of it is on the back side of the mirror, and on your side, the right one is on the front side of the mirror. And additionally, I can control with the other mirror the light which is reflected back. Here I'm just turning the screw on your right-hand side, so the reflection of this mirror can be aligned. And of course, we need to align it to be parallel to the incoming light and to go correctly into the center of the incoming light beam. That's what I did. On the other side, we have now one light beam passing through the first mirror. It is reflected, going to the first mirror again. And now I need to align this mirror in order for the reflected beam, 2 times reflected beam, to go parallel to the incoming ray. And that's when I look either at this mirror, the other one, or simply look at the wall. Here we are. And yeah, there is my laser. And additionally, here, turning the screws of the mirror on your left-hand side, I can have a second spot which is able to move. And when I just try to focus and keep my hands off the system, you can already see there is some fringes around it. And when I just touch the mirror, you can see these fringes disappear or move. So there is already an interference going on of the incoming and reflected light. So we have just set up, some call it a Fabry-Perot étalon, others call it a resonator, whatever. It's just light beams coming from my laser pointer, interfering with each other. And in the end, it shows me that my mirrors are sufficiently parallel. And now I have a resonator. I have a discharge tube. I can just put it in, fasten the screws, switch off my pilot laser, and switch on the discharge tube. And with a little bit of fine adjustment, the laser is working. Sorry, camera failure. No, we didn't cheat at the moment. Okay. Sorry, so zoom to the wide angle. And here you can see laser is on again. And if I put my fingers on the screw and turn them around a little bit, you can see it probably best here on this reflection coming from the Brewster window. The laser can be easily turned on and off, and it's just the alignment of the mirrors which are responsible that the laser itself has a resonator, and the resonator is aligned with my discharge tube. So now I can take the other mirror and move it back and forth a little bit. And can we go to the camera? And if I do it in a more or less controlled way, I can always find back the position where the laser is still working. So I can change my resonator length. A little bit of tuning is necessary, but it's easy. Oops. Here we are again. So it's easy for the students, since we have a completely separate setup consisting of the tubes and separate mirrors. So it's easy for the students to work with this laser. And yeah, for the time of half an hour, I can sadly not show every experiment. So we'll have some experiments we can just talk about. And so the first one is just setting the laser up from scratch and learn what alignment means. And included in this is something like the beam waist and the laser beam diameter. So when you have a close look at our mirrors, you will notice that this mirror, which is a flat one, not really in focus. So this one on the flat mirror is a rather small dot, but on the other hand, when I turn around, the spot on the other mirror has a much larger diameter. Well, that's because we have an asymmetrical configuration, and in this configuration the flat is where the beam waist is, so we have the smallest diameter right at this mirror, and students can first take their eyes, but yeah, it's really as easy as camera 3. Taking a caliper and measuring the diameter of the laser beam until it's switched off, and just replace my fingers with a caliper. And yes, so the beam waist can be measured. And the next one of the experiments would be that we have some modes. Transversal electrical TEM00 is a normal mode this one is working on, but we can easily put a hair inside our resonator or a wire or whatever you like, and suppress this TEM00 mode and go for a TEM01. Looks funny, and students can learn that the resonator is not a one-dimensional thing, but it's got a two-dimensional profile, and maybe you can use a beam profiler camera or whatever. Then next one is when we go for the experiment and we are talking about the distance of our mirror. You remember I was able to move just my mirror back and forth, and you can see it here. The laser is going on and off, but at a closer distance it's much easier to run, simply because this is a mirror which has a radius of curvature of approximately 700 millimeters, and stability tells me with a flat on the other end it's about 700 millimeters, and then the laser goes off. But we can swap the 700 millimeter one for a different mirror, which is called, other way around, which is called 1000 millimeter. And just having a close look at it, this is the mirror itself, and as you would expect, it's a dielectric mirror, and this mirror has a radius of 1000 millimeters, and when I swap it for the other mirror, the laser will run up to a resonator length of 1000 millimeters, not 700 as before, So students can learn that it depends on the radius of the mirror and what is going on there. So next one, yeah, some more advanced topics. We could put in a thing called a litroprism, looking like this, which is an angled prism having a mirror on the other end, and so wavelength selection is possible. We can swap the red laser light, as you can see right here, somewhere, and the red can be swapped for a yellow one just by introducing some wavelength selection into the setup. And there is another one which is called a birefringent tuner. And this birefringent tuner is just a plate made of quartz put into the resonator at the Brewster angle, and then I can change the polarization of a beam, and under certain conditions the laser starts to go on again, and with that we can select two other reddish lines of this laser, and so on and on. Another experiment we can do is again vary the distance of our two mirrors. But what happens inside such a cavity is that there are a nearly infinite, but a very well-known number of waves as a standing wave. It's a resonator. So my wavelength is 632 nanometers, and inside this distance there are several billions of light waves. But the distance and the spacing of such a light wave is approximately 200-300 megahertz, and the gain profile of our helium neon is approximately 1.5 gigahertz. So it is possible for several longitudinal modes to coexist in the laser, and it will. And then we can use an electrical detector, which is simply put on the optical bench. Okay. At the optical bench, looking into the laser beam, and the other end of this is connected to an amplifier and to a spectrum analyzer, an electrical spectrum analyzer. And what we see on this electrical spectrum analyzer is an electrical beat frequency of approximately 200-300 megahertz. And it's just simply because C over 2L, we have 70 centimeters of resonator length. C over 2L, oh well, that's 1.5 meters. And speed of light is 300 million meters per second. So divided, it's just about 200 megahertz. It's a nice experiment, but time is running. Sorry. And what we can even see if we zoom into this mode beating frequency, there is a frequency pulling. So you might think of the gain medium having a shape like a Gaussian shape, 1.5 gigahertz wide, and we have several lines in between, and these lines are pulled a little bit slightly, the resonator lines are pulled a little bit inwards, and that gives me a frequency pulling of something like 100 kilohertz or so. If you would like to see, maybe we can do another webinar on that. Okay, so that's from the very basic scratch of the helium neon laser to very advanced topics in theoretical laser physics. Talking about safety now and then, laser light is not dangerous by itself, but a high intensity light is dangerous, and that's why we have something like an IEC 6825 regulation. And for our helium neon laser, with best alignment and a lot of time, you can achieve something like 3 milliwatts of output power when you're using a special output coupler. When you're not using this output coupler, there is no way to go beyond class 2. So if you just keep this output coupler, just don't order it or just keep it locked, so the students have no chance at all to get beyond class 2. And that's quite nice. They can work with a laser without legally having to think about eye safety. and they can use it with protective glasses. Of course, for their better feeling, you might want to use alignment glasses, which reduce the light a little bit. But in the very end, with a special output coupler, we can come right close to this class 2. And so you have the choice whether you want a really high light output or you want to have something that is safe for the students and can be used in the lab. There is another set of mirrors which makes it operating in the infrared, and well, that's really high intensity and not recommended for student use. And now for the next one, we're talking about the neodymium. And while this sheet is shown on display, I'm gonna realign my setup a little bit. Thanks. Colleague is taking all the parts. I have a second setup prepared right here. And yeah, well, maybe we can even show what I'm doing right now is I have a small setup. You saw already the PowerPoint with the neodymium laser. I need a power supply, of course, and the setup of it is on your left-hand side with a yellowish mark on it is a diode laser, which can be part of the experiment itself, looking at the output of such a diode laser, but we can simply use it in this setup as a tool to power our YAG laser. And yeah, safety regulations require me for the power supply to have a lock, and the lock is just made by entering a pin number. And now power supply is checking that everything is fine. So in order to make it run fast, let's just set some parameters. And maybe you can already see it's running at bright green. And so what else did I want to switch? I wanted to switch on some kind of frequency modulation. And as you can see, I hope you see at least some flickering. Looking at the receiving computer, yeah, it looks like it's flickering on your screen too. What I see here is an 11 Hertz modulation of the pump laser, and we get a green laser light coming out of here. So talking about laser safety once more, this pump laser is a class 4 laser. So regulations tell me I should wear glasses. Okay, these will absorb the infrared radiation involved in this setup. And now, same story as with the helium neon. Let's take it apart and reassemble it. And first of all, yeah, so just a filter holder. We have our mirror structure once again on these two parts. In between is a frequency doubling crystal, second harmonic generation. And now, having removed all these things, I have my infrared laser beam going on here. And since it's infrared, it cannot be seen with the naked eye. And if I now take apart all the components, you can have a look at the direct, laser beam coming from the diode. And it's by no means a laser beam. It's a thing which has a more like a fence-like structure. And maybe we can even use the infrared sensitivity of my camera in order to take a look at the diode. At least it sees something, and let's put a sheet of paper in there. That works fine. Because this camera is much more infrared sensitive than our naked eye, I can use it to demonstrate what's going on here. And yeah, the reason why this happens is quite simple and can be best explained in a short slide. We have a diode laser here, which is a semiconductor structure, and it is a very small semiconductor structure in the end. So it's just about 2 or 3 microns wide, and what we get is a diffraction at the output of this laser diode. It's a waveguide, but the diffraction widens up the emitted light to this 40-degree angled cone, which you saw right a few seconds ago. And so to make it a real laser beam, we need to have something of a lens which will focus it back to a laser beam. And this is called a collimator, and okay, we are at the 2 micron spot. So we need something more like just an ordinary spherical lens, and this can be in the old days a triplet. Nowadays a molded air sphere is a better way to do. And so we can go back to the life. We have our laser, which is expanding. And now we take our first component in, and to be safe, I shall put in something as a beam block, then I can remove it. Now I know that my laser beam is, can we go to camera 3? My laser beam is somewhere over here, and I can start to focus it. Make it a real laser beam out of it, which has a constant, well, okay, a little bit better focusing, a constant diameter over the length. Yeah, something like this. Well, good enough for our setup here. And the good thing about the neodymium YAG is there is so much gain. This kind of laser doesn't really care about precision alignment. You can just put it on the bench and that's it. So now we have a focusing lens, and this focusing lens will give me a focus somewhere, and just trying to find it. Okay, so it's expanding. Here we have kind of a focus. Oh well, quite close for the camera. Here we have a focus, and if I accidentally put some black paint in the focus, it should start to create some smoke. Yeah, there we are. So talking about the power of this laser and exactly where the spot is, where the focus is, that's of course a point where I want to place my neodymium YAG crystal. Looking at the bench, it's approximately at 14 centimeters. So I will put my neodymium YAG crystal there, which is, by the way, looking just like a piece of glass, having the mirror on one side. Well, placing it right here, putting the second mirror on the other side, and hopefully we'll already have some laser action in the end. And to verify this is a real laser, we have an absorption filter which will block the 808 nanometer of the pump laser and let through only the 1064 nanometer of the working laser beam. And as easy as putting the components together, it's already working. I could try to optimize, but I can just try and insert the second harmonic generation part. And we'll see there is already green light coming out. And now we can take the screws and optimize laser function just by turning on this, no, wrong direction, turning on these screws until we are satisfied with the result. Other things to change are the angle of our KTP crystal, which does the second harmonic generation, and so on. So there are a lot of screws, but this one does not need precision alignment. It's just put together, and students can have their green laser operating almost within a minute. And now we can start, if time permits. I'm a little bit over time already. If time permits, we can take our oscilloscope, take some kind of detector, put the detector on the optical bench, cable everything together, switch on the oscilloscope, by the way, connect the cable to the amplifier, and then we can have a look at the timing of this laser beam. Okay, something is visible, but I should better get my small camera here. Here we are. Hope you can see the oscilloscope screen. And as with any modern oscilloscope, just press auto set and you're done. And yeah, I was modulating my pump laser at 11 Hertz, so it's switching on and off in a regular interval, and that's exactly what you can see. It's off when the output is low, and now I can have the oscilloscope and zoom in on the very detail. Should do some more alignment, but you can see right on your right hand side there are some spikes, and that's exactly what happens at the very beginning. When the laser is turned on, there is no laser light inside the resonator, but the laser is just starting up, and starting up means in this case some kind of instability. So the population dynamics is working, and you can see those peaks on the right hand side where the laser is just starting. And now I'd like to increase light output a little bit. Maybe we can get a better view of that spikes, but for the moment some more, but not higher ones. I just want them to be a little bit higher. There is one. Okay, this is the very first, now in the center, this is the very first startup of this laser. And with a little bit more time, things can be improved, but since I'm already talking 40 minutes now, well, time to come to an end, sorry. And so we'd like to do a short sum up of the neodymium YAG, which is this structure. You will get this whole document as a PDF in a minute. And so we can talk about the threshold of every system. We can talk about the absorption lines of neodymium YAG. When I change the temperature of my diode laser, it changes its wavelengths. And we can vary the absorption. We can have a look at the timing of the free emission just by placing the detector close to the crystal, not using any resonator. We'll see it's 250 microseconds. We have just seen the spiking, and we can have a look at the timing on turn off and so on. Safety, yeah, you saw me wearing glasses, so this is a class 4 laser, and students have to take some measures. Of course, we do have written instructions for all these, and the tasks are how to set up a laser on an optical bench from scratch. Students can really feel each component. It's easy to align and start up, so we can do it in presentation in a live webinar. Parameters can be changed easily and so on. And yeah, one thing I didn't just mention, cleaning of optical surfaces was quite necessary. Yesterday evening I cleaned everything, and so